All right, so let's go over another set of notes. These are the notes on action-reaction forces. Okay. So far we talked about, in the last chapter, we talked about Newton's first law. Newton's first law was the law of inertia, and the idea that objects are going to do what they're doing. If an object is sitting still, it's going to stay sitting still. If an object is moving, it's going to stay moving in that direction until, for both of them, until another force acts upon it. All right, so the kickball that's just sitting still, it's not going to do anything until you exert a force and kick it. When you kick it, then it's going to go do something. All right, and then if you have a kickball and you throw it, well, it's not going to go forever. It's going to ultimately slow down because of friction on the ground, or because somebody catches it, or it runs into somebody. All right, so somebody else exerts another force on it, or friction exerts a force on it. Okay? That was Newton's first law. Newton's second law says that if we exert a force on an object, then that object is going to accelerate in the direction of that net force. So what is that? Kickball sitting there. We kick the ball. What's it going to do? It's going to accelerate. It's going to go in that direction. That's what Newton's second law says. All right. So it's as long as we exert a net force, all right, a force that's greater than the force that's just holding it still, then it's going to move in that direction. All right. That was Newton's second law. Now we're on Newton's third law. All right. And Newton's third law says for every action, there's an equal and opposite reaction. All right. So what my examples are is, imagine if I'm sitting in a wheelchair and I got a bowling ball and I'm going to throw a bowling ball. All right. Well, a bowling ball has a lot of mass. If I take that bowling ball and I throw it in a wheelchair, where am I going to go? I'm going to slide backwards the other direction. Why? Because in order to push that bowling ball that direction, there's going to be a force in the other direction equal to the amount of force that it took to push it that way. All right. So I'm going to roll backwards. All right. Another example of that is a gun being shot. If you ever shot a gun, when you hold the gun up to your shoulder, when you go bam, hit it, what hits back here? Well, the back of the gun ends up kicking back and hitting you in the shoulder. Well, that kickback, that's the reaction force of the force that causes the bullet to go that way when you're hunting or anything like that. All right. So action-reaction forces are that idea. Getting a rocket to take off and go up in the air. Right? In order to get that thing to go this direction, we got a force that's going that way. Well, there's also going to be a force in the opposite direction pushing on something. And that's the gases that come out the bottom of the rocket pushing on the air that's below it, causing the rocket to take off and go up. That's an action-reaction force. Okay? So on this idea, how does an action-reaction force, how is it not a balance force? Because we have a balance force, remember, was the idea of a tug of war, where I've got a team over on this side and a team over on this side. They're both pulling on the rope, and they're pulling with equal force, and the rope doesn't move. All right. Well, know that they're both exerting a force on the rope. All right. This team over here is pulling on the rope. This team over here is pulling on the rope. So they go, and they pull really, really hard, and nothing happens. All right. So that's not an action-reaction force. All right, that's a balanced force. Now, with an action-reaction force, I'm going to use the gun idea. Right? For me to shoot a gun, well, the one force is exerted on the bullet, causing the bullet to go that way. Right? The other force is exerted on the gun, making the gun go this way into my shoulder. Right? So instead of being on the same object, it's on two different objects. One force is on the bullet, one force is on the gun. Right? Different than a balance force where both forces are on the same object. Right? The rocket going up in the air. Right? The one force causes the rocket to go up. The force is on the rocket. The other force is down on the air, the molecules below. So we end up with that opposite force, which causes the rocket to go up. Okay? Taking a bowling ball and tossing it. One force is on the bowling ball to cause the bowling ball to go that way. The other force is on me, causing me to go back this direction. All right. So the forces are on two different objects. That's the difference between a balance force, and an action-reaction force that we're talking about today. All right, second one, letter B, says momentum. Now the little P that's in parentheses behind that in your notes, that's the symbol for momentum. I know it seems crazy. Why in the world is it a P? I personally don't know, but that's what they ended up choosing. I will say, well, they couldn't use M because M is mass. All right, so they couldn't use M for momentum. So they had to come up with something else. I'm going to assume it's probably a Latin name for momentum, probably starts with a P, but I don't know that for sure. I'm going to be guessing on it. All right, so what is momentum? This is a property of, and I put in big capital letters, a moving object due to its mass and velocity. Momentum is just like inertia, all right? And the idea that an object's going to do what it's doing, except it's got to be moving, all right? Inertia, remember, an object that's just sitting still can have inertia, but an object that's sitting still does not have momentum because it's not moving, all right? So it's got to be moving. Says no, similar to inertia except moving, and non-moving objects have inertia, but only moving objects have momentum. All right, so momentum, it's got to be moving. Hey, there's an easy way to remember it. Moving momentum, moving momentum. All right, versus inertia is not moving. All right, now letter C, which has greater momentum. All right, so greater momentum, we got a toy truck traveling at 5 meters per second or a real truck traveling at 5 meters per second. So both going the same speed. All right, which one's got more momentum? Well, it's going to be the real truck. Why? Because it's got more mass. Got greater mass, it's going to have greater momentum. It's going to be harder to get it started. It's going to be harder to get it to stop. Right? So it says there the answer, the real truck, because it has more mass. Greater mass, greater momentum. All right. Letter D says, why can't a person stop a moving bullet? Well, a moving bullet's really small. It's not very big. It doesn't have very much mass. But obviously, no object can stop a bullet. All right, unless it's really big, like big pile of sand, a brick wall. All right, but small little things can't. Why is it? Because that little bitty bullet's got lots of velocity. It's going really fast. Because it's going so fast, it's got so much momentum. It's really hard to stop it. All right. So underneath letter D, it says low mass but very high velocity. It's going really fast. All right, if it's going really fast, that means it's got lots of momentum. High velocity, high momentum. All right. Letter E, why can't you stop an elephant from walking? Oh, an elephant. Elephant's got lots of mass. Not going very fast, right? Once it's moving, good luck trying to stop him, all right? Because he's got so much mass, it's going to take a lot of energy, a lot of force to get him to stop. So even though he's got low velocity, not going fast, he's got large mass. So large mass means large momentum, all right? All right, momentum can be transferred. We can take momentum and transfer it from one object to another object. But what's got to happen? Boom, they got to hit each other. All right. So think of the idea of pool balls. If you go play pool, in order to get the 8 ball in the corner pocket, you got to take the white ball, the cue ball, and get it to hit the 8 ball. When it hits the 8 ball, then that momentum, that moving momentum of the white ball is going to be transferred into the black 8 ball, which is going to cause the 8 ball to hopefully go right in the corner pocket, and then you win. All right. So, or another thing, which I have one here, is a Newton's cradle. All right. And with a Newton's cradle, the concept behind this is if I pull this guy out, if I let go and let him come down and hit the other ones, what happens? Oop, let me see if I can hold it still so they're not swinging back and forth. So notice when I let go and it hit this side, it caused one on the other side to pop out. Why did it come out? Because it transferred the momentum from one side to the other. All right, so all we're doing is a transfer of momentum. So that momentum actually goes from this ball to the next one, to the next one, to the other one, and then it doesn't have anything to transfer it to, so it goes out. All right. What happens if I do 2 of them? Well, if I do 2 of them, then notice that it actually transfers it to both of them on the other side, and both of them take off. Oops, that kind of didn't work out. Try it again. Try this again. We'll do 2. There we go. All right. Now it doesn't work perfect because I'm holding it up in the air, but these things are called a Newton's cradle. Why is it called Newton's? Because it shows Newton's law. That's why. So the second one underneath there says when one ball hits another, the second ball moves and the first ball stops. That would be like the idea of a pool ball, or even with this thing, that the first one stops, it loses all its momentum, and it transfers the momentum to the other side, and they take off. Then there's the law of conservation of momentum. It says the total amount of momentum of a group of objects, like the balls in the Newton's cradle, does not change unless an outside force acts on the object. And I've always had students tell me that, why does this thing stop? I always thought they should go and go and go and go and go forever. They should just keep going and going and going, but it stops. Why? Well, there's got to be some other force in there that's taking force away from these. Well, what is that force? Well, that force is friction. friction is occurring. Because these balls are hitting each other, they're exerting friction, and there's some heat being produced, and that heat's going floating off into the atmosphere. So we lose energy to friction in the form of heat. There's also some friction up here in the top where where the strings touch each other. Right. So if we could get rid of all of the friction in this thing, then it would go and go and go and go and go forever. Right. But we can't get rid of friction. There's always some source of friction inside that motor. If you can ever come up with a way to get rid of friction, give me a call. Right. Because we're going to like be rich. Right. Because we'll be able to make motors go and go and go forever, and everybody will want our motors, and we'll be rich beyond belief. Right. But currently right now, there's no way to get rid of friction. All right, well, my next page of notes on here is just a little bit, and that says, but why does the pool ball or the Newton's cradle stop moving then? That's what we just talked about. Why? Because friction removes energy as heat, right? And that's why everything that's out there, there's nothing that goes forever because there's always some friction that's occurring, right? And we try and reduce that friction as much as we possibly can by oiling things, making it so they don't touch each other. If we can do that, then we can reduce friction and things will go longer and we get better efficiency out of it, which would be like our cars. If we keep our oil changed, then we get better efficiency and we get better gas mileage, right? But we're still going to have some friction. We can't get rid of all of the friction. All right, well, that finishes our notes on action, reaction forces. And my last thing I want to point out, remember the difference between these, action, reaction, and a balance force, a tug of war. So tug of war is both on one object. They're both pulling on that rope. On action, reaction, then they're actually applying it to two different objects. The gun, one force goes on the bullet, the other force goes on the gun and kicks back. It's on two different objects. Right? So that's the difference between those two things that we've been talking about ultimately. Well, we'll see you in the next thing. Talk to you later. See you. Have a great day.